Hello viewers, continuing with our discussion on inverse trigonometric functions, today we are going to focus on properties of inverse trigonometric functions. But before that, let us just do a quick recap of the work done so far. We discussed in our earlier lessons that though sine, cosine and other trigonometric functions are not one over their domains, but when we restrict our discussion to some specific sub-intervals, the functions can be made 1 and when mapped to their respective range, they become onto as well, and thus they are invertible, but restricted to some specific sub-intervals. This discussion also gave rise to the understanding of some specific branches known as the principal value branch of inverse trigonometric functions. What you have now on screen shows you a table of all the possible 6 inverse trigonometric functions with their principal branch. These principal value branches will remain with us as our discussion progresses. We also discuss that the definition says that sine inverse of x is y if x is sine y, which also gets interpreted as that sine inverse of sine x is x where x comes from the closed interval minus pi by 2 to pi by 2, and also sine of sine inverse x is x where x belongs to minus 1 to 1 closed interval. Is there something specific that we are looking at here? Yes, the x that we have chosen, which belongs to minus pi by 2 to pi by 2, restricts our discussion so that the inverse is defined, and that is what happens for the other inverse trigonometric functions as well. So, take a quick look at what we have here. Cos inverse of cos x is x only if x belongs to the closed interval 0 to pi. Cosec inverse of cosec x is x when x belongs to the closed interval minus pi by 2 to pi by 2, not including 0. Similarly, for the other 3 inverse trigonometric functions, you have the conditions defined. Will we ever need this? You may ask. Why can't I just say sine inverse of sine x is x and get away with it? Well, if you come across a question which could be possibly a 1 mark, but then you know how important that could be. If the question says evaluate cos inverse of cos of 13 pi by 6, and you jump up and say, well, that is 13 pi by 6 because cos inverse of cos x is x. Well, then you have to stop and watch and say or think that 13 pi by 6 does not belong to 0 to pi close interval, which is the principal branch for cos inverse x, and therefore, the definition does not allow us to write this equal to x. But at the same time, we have learned that 13 pi by 6 can always be written as 2 pi plus pi by 6, and cos of 2 pi plus theta is cos theta. Cos 2 pi plus pi by 6 is nothing but cos pi by 6. We learned all of this in grade 11, and now we are ready to say that cos inverse of cos 13 pi by 6 is same as pi by 6. So, you may need these relations, conditions as we progress further down as well, but this itself can be an important 1 mark question for you. Now, there are certain properties that are listed in your NCERT textbook. Today, we will not be discussing the proofs of these properties, but it is important for you to understand why these properties exist. So, I will suggest to you that you do look at the proofs from the book, but today we will first go through the properties and then consider their applications, which are often tested in exam as well. To begin with, we have the first property which says that sine inverse of 1 by x is cosec inverse x, where x has the restriction x must belong to the interval over which the cosec inverse is defined. So, x must be greater than or equal to 1 or x is less than or equal to minus 1. Similarly, you have 2 more properties which says that cos inverse 1 by x is sec inverse x, tan inverse of 1 by x is equal to cot inverse of x. Somewhere as you look at the property, you must be able to feel as to where this is coming from. Remember, there is a relation between cosec theta and sin theta. Keep that in mind. When you look at the proof, you will be able to relate and see how the two gets connected. What does our second property say? Second property says that sin inverse of minus x is equal to minus of sin inverse x, where x belongs to close interval minus 1 to 1. Cosec inverse of minus x is minus of cosec inverse x, where x is greater than or equal to 1 or x is less than or equal to minus 1. Tan inverse of minus x is minus of tan inverse x, where x belongs to real numbers. Again, if you are with me, you would have realized that somewhere there is a relation of what we learned in grade 11 as sine of minus theta is minus of sine theta. So, you can see some likeliness there. Now, I would advise you to just sit and try out the proof so that these properties stay with you longer. What happens if I have cos inverse of minus x? Well, cos of minus theta was not minus cos theta. So, cos inverse of minus x is not going to be minus of cos inverse x. So, watch out for it. It is same as pi minus cos inverse of x. Similarly, sec inverse of minus x is pi minus sec inverse x. Cot inverse of minus x is pi minus cot inverse of x. The fourth property, sin inverse of x plus cos inverse x is pi by 2. Cosec inverse x plus sec inverse x is pi by 2. Tan inverse of x plus cot inverse x is also equal to pi by 2. Take a moment. Where is this coming from? Do you see any underlying condition in the trigonometric functions which can help us to reach this result? I think you are thinking of cos of 90 minus theta is sin theta, and that is where the connection comes. Let us take a look at our next result. The fifth property, it is one of the properties in fact which you will find yourself using many a times in this exercise. So, keep a watch on this. Tan inverse of x plus tan inverse y is tan inverse of x plus y by 1 minus x y, and to keep things defined, this is only true when x y, the product x y is less than 1. Tan inverse of x minus tan inverse of y results in tan inverse x minus y by 1 plus x y is greater than minus 1. And the third, twice of tan inverse x is equal to tan inverse 2x by 1 minus x square. X must be strictly between minus 1 and 1. Again, the formula behind it, which you learned in 11th standard, comes to use. Tan of a plus b is equal to tan a plus tan b by 1 minus tan a tan b. So, if you start the proof by taking say tan inverse of x to be a and tan inverse of y to be b, in 3 steps straight away you would be able to reach the other side. I will leave the proof for you to figure out, but we will be using it today again and again. So, look out for it. The last, the sixth property in your textbook suggests that twice of tan inverse x is equal to sine inverse of 2x by 1 plus x square, where again there is a restriction on x for the function to be defined. So, mod of x is less than or equal to 1, and twice of tan inverse x is cos inverse 1 minus x square by 1 plus x square, where x is greater than or equal to 0. Again, if you think about a relation where you have sin 2 theta connected with tan theta, you will get the proof for this. Sin 2 theta is equal to 2 tan theta by 1 plus tan square theta. One of the formulas we grilled and drilled in grade 11, you must have perfected it there. It is going to come in use here, and many more results that you learned in 11th standard are going to be used in this and further down more chapters. So, if you have certain weakness about trigonometric formulas, well, it is time to brush them up. Let us start looking at the applications. How are we going to put these properties to use? One of the very favorite questions that you would come across again and again is right here. You have to prove that tan inverse 1 by 5 plus tan inverse 1 by 7 plus tan inverse 1 by 3 plus tan inverse 1 by 8 all adds up to be pi by 4. Now, you can see there are 4 terms with tan inverse in it, and we just discussed tan inverse x plus tan inverse y. So, why not take two terms together at one time and apply the formula? Why do not you pick up a pen and start off along with me? If I start from the left hand side, this is what I would get. Tan inverse of 1 by 5 plus tan inverse of 1 by 7. Applying the formula would give me tan inverse 1 by 5 plus 1 by 7 by 1 minus 1 by 5 into 1 by 7. Similarly, apply it on the next two terms. Now, it is a simple basic calculation which will lead you to tan inverse of 6 by 17 plus tan inverse 11 by 23. So, starting with 4 terms with tan inverse involved in it, now we have come down to 2 terms, but still with tan inverse. So, what should we do? Apply the formula again and see what you get. So, again I have tan inverse of x plus tan inverse of y, which becomes same as tan inverse x plus y by 1 minus x into y. Little bit of calculation will give you tan inverse of 325 by 325, which is nothing but tan inverse of 1, and within the principal values tan inverse of 1 will give us pi by 4, and that is what we wanted to prove as our right hand side. Wasn't that simple enough? So, the only thing is to know the right formula and to have the presence of mind to use it at the right place. Let us try another situation. The question says, prove that tan inverse 63 by 16 is equal to sin inverse 5 by 13 plus cos inverse of 3 by 5. Now, what do you see different in this problem, keeping in mind our first question that we did today? There is a tan inverse on left hand side, on right hand side you have sin inverse and cos inverse terms. We did not learn any formula where we had a sin inverse of 5 by 13 plus cos inverse 3 by 5 getting combined. We only had something like sin inverse x plus cos inverse x is equal to pi by 2. So, to begin with, there is no property readily available which you can just apply. You need to work on it, and the best would be if I start with right hand side and try to write it all in terms of tan inverse. So, the main task here is to rewrite sin inverse of 5 by 13 as tan inverse of certain fraction. How would one do that? Let us go through this process, follow it carefully, and you will realize that it is really not so challenging. Starting with the right hand side, which is sin inverse 5 by 13 plus cos inverse 3 by 5. Begin by assuming sin inverse 5 by 13 to be, say, a quantity x and cos inverse of 3 by 5 to be y. The moment I have that, then the definition allows me to write that if x is sin inverse 5 by 13, then sin of x must be 5 by 13 and cos of y must be equal to 3 by 5. Now, you must know that if sin x is 5 by 13, cos x can be calculated. How? Using the fundamental trigonometric identity. So, sin square x plus cos square x is 1, and you can use that to find what cos x and similarly what sin of y is going to be. And I have that calculated here for you, but also if you are good with Pythagorean triplets, it just takes a minute to figure out what the other t functions are going to be. So, cos x is 12 by 13 and sin of y is 4 by 5. Now, why did I calculate cos x and sin y? I had sin x and cos y, because I can now find out what is tan x and tan y. Tan x is going to be nothing but 5 by 12, tan of y is 4 by 3. Once I have the values of tan x and tan y, do you think you can find what is tan of x plus y? Surely you can. Why don't you work it out? We have tan of x plus y is equal to tan x plus tan y by 1 minus tan x tan y. Substitute, solve, and you get 63 by 16. And so, we are ready to have tan of x plus y equal to 63 by 16. X plus y therefore is tan inverse of 63 by 16. What was x? Nothing but sine inverse of 5 by 13, and y cos inverse of 3 by 5, and hence your problem is solved. So, it was not so very challenging, isn't it? Just keep your calm about it and I am sure you will get through it. Now, let us just take a very interesting problem. It is actually given as a MCQ question in your NCERT. So, suppose I say it is only a 1 mark question, can you do it in a jiffy? Surely you can. Look at this, I have tan inverse x by y minus tan inverse of x minus y by x plus y. To evaluate it, one way is I can just use the formula directly, the property, but the other is interestingly very simple, and here it is. You can always write the second term as tan inverse of x by y minus 1 by x by y plus 1, divide both numerator and denominator by y. And now again applying the property as tan inverse of x by y minus tan inverse of x by y minus tan inverse 1. On simplification, that is nothing but just pi by 4. So, as you saw, the 6 properties do help us in simplifying and working with inverse trigonometric functions. We will be continuing with more applications of these properties in our next lesson. Stay tuned.